In this video, I'm going to do problem 5.78 out of your textbook, and 5.78 says to model problem 519. So that's what I'm going to do. I'll just put that text over there. By the way, you can place text using that menu item. So that's what I did. So the first thing is I look at 519. 519 has an op-amp in it. It doesn't tell me what op-amp to use, but let's just use a generic LM741 or 741 op-amp. So place component. Oh, you probably have it looking like something like that when you first sign on here. Different things. So I wasn't sure where op-amp was. So when I'm looking at all groups, it was hard for me to find where the 741 was. So I just decided to do a search, and the function is op-amp, but the component is a 741. So I will search for 741, and the 741 op-amp will come up. So I'll say OK, and then I want to show you a few neat things about that. So here's a 741 right there. This is the symbol for it. But I can look at how it's modeled. So if I say view model, here's the SPICE model, or the PSPICE model that your text talks about. So underneath multisim is a SPICE model. So a few things that I can see about it is it tells me that it's expecting to operate with plus and minus 15 volts. That's your VCC and your VEE. I bet there's no way I can make this bigger. Let me try Control++. Nope, doesn't work. It also says my input resistance is 2 mega ohms right here. This is the input resistance. It says 2e to the plus 6. So input resistance is 2 mega ohms. Looks like output resistance is 75 ohms. The open circuit VOS would be V open circuit is 0.001 volts. I short circuit is a very small current. And there's a common mode rejection ratio, which we haven't really talked about yet, but that's how good it rejects the common noise to both terminals. So the whole internal model for the op-amp is hidden here underneath, and it is a SPICE model. All these modeling programs have SPICE underneath. It's kind of interesting. Okay, so there's your model. A few other things. If I have detailed report, it gives you some information about the component in the database. It belongs to the op-amp family. It's in the analog group if you were to look for it under the master database. There's a gain bandwidth product, offset voltages, slew rates, a lot of good information that's practical. It models just exactly like the data sheet would model it. So here's the symbol for it, and it looks like it repeats the SPICE model there. This is the footprint. This is, if you're doing a PC board layout, this is what the package actually looks like. So poke around, look at all of these things. It's good information to know. But yes, this is the model I want, so I'm going to put it, or the device that I want. So I'm going to say OK. There it is, and I'm going to place it. And for me, if I push the escape key, I stop placing. So let's look at it a little bit closer. So now I have an op-amp, and these are the pin numbers on the op-amp, but we want to relate it to a real op-amp. There's the non-inverting input and the inverting input, and it doesn't say what these other pins are, so we need to look, and this is the output. We need to look at a data sheet and figure out how to connect this op-amp. So let me find that for a minute. I'll find the data sheet. So I just Googled LM741, and I got the data sheet from on the internet. So let me make this a little bit bigger here. So this shows you that my LM741 can come in a round TO99 package, which is a metal can package with the legs hanging out the bottom. It can be a surface mount package with these kind of leads, or the one that we'll have in lab will be a dip package, which looks like that. So now it has all of the different pins labeled, like the inverting is number 2, non-inverting is number 3, tells you what Vout is, and then it has 2 pins called offset null, and then it has your plus voltage right there. The plus voltage right here is where you're going to connect up plus 15 volts, that's pin 7, and the minus voltage right there is at pin 4. So notice it has a plus and minus voltage here. So what do we do with these other pins, these offset null pins as they're called? Oops. So that will be our question, is to look at what to do with offset null at this moment. So we'll continue on the data sheet and look at things that you can do with it. So it tells you what offset null does. I just saw it a moment ago what the offset null does. Here's the offset nulling circuit. So this is telling you what you need to do with it, but it has to do with getting rid of the little offset voltage offset that's between the plus and minus input pins. So I'm pretty sure that you can not connect the offset null at all, and that the op amp will still work. If you are doing something that's very close to 0 volts, then you have to get concerned about the offset null. So let's check back at our data sheet for a moment and see where the plus voltage needs to go and the minus voltage, which I should have noted and I didn't. Open that data sheet back up. The plus voltage is 7 and the plus voltage is pin 7 and the minus voltage goes to pin 4. So we need to remember that. The plus is pin 7 and the minus voltage is pin 4. So let's power the device up first. The device will not work unless you power it up. So let's place some power for our op amp. I'm in sources. I need power sources. So DC power. I think we can do this actually. I think this actually works to do VCC. Oh, it says it's a TTL supply. Nope, it's not going to let me. Okay, so let's just do DC power. So I need to give it plus 15 volts and I'll need to give it minus 15 volts. So I just place those two components. This one I'm going to change to 15 volts. And this one is I'm going to change also to 15 volts, but it all has to do with how I connect it. And then I need to place a ground, place component, power sources, I need a ground. Simulation doesn't run without a ground. So I'm going to ground the minus side of the plus 15 volts. But on my minus 15 volts, this is what I'm going to do. So I'm going to flip this guy, flip horizontally. No, I guess that's not the plane. Flip vertically. I'm going to connect the minus right there, the ground, to the plus side of it. So if the plus side is connected to ground, then the minus side is 15 volts below the 0 reference point. So that makes this be at minus 15 volts. So I will connect that, and I will connect that. And I don't need to connect the offset null for this circuit to work. So let's draw the rest of problem 519. So it says that the non-inverting pin has to go to ground. Oh, I just noticed something else. If I want to draw it just like the circuit here is drawn in your textbook, it has the inverting pin on top. So I just want to flip this. So now it looks like the textbook. I'll be in the same orientation as the textbook, which means that this guy goes up here, that's minus up here, and this one is plus, goes down here. Connect the plus to pin 7, that's good, and the minus to pin 4. That's good. And now I'm looking at the textbook problem. It says I want the plus to go to ground also. I'm just going to do a Control C, copy and paste. Put my ground to pin 3. And the rest is putting components that we already know about. So I'm going to pause this a moment. You don't have to watch me place all the components. And then I'll come back after I've placed all the resistors around here and we'll look at how to run the circuit. So here's the final problem all drawn out in Multisim, and the input voltage is 750 millivolts. The only thing I did different from the textbook is add the power plus and minus supply power to the op amp. I didn't connect the offset nulls, and instead of connecting grounds all together explicitly, I can put ground points at each one of the points, and it's the same thing to this simulation. And problem asks you to find the output current here. So I just put my probe on that spot and I get 560 microamps, which is the answer in the back of the book.